Good morning. My name is Jiratvik. I am from CSC series section. My ID number is 21951A05G2. Today we are going to see data structures. My topic is as such, what's in a name? A search algorithm. Motivation to approximate the shortest path in real life situation like in maps games where there can be many hindrances. We can consider a 2D grid having several obstacles, and we start from a source cell to reach towards a goal cell. What's in a search algorithm? A search algorithm is one of the best and popular technique used in pathfinding and graph traversals. This is the picture for the a search algorithm. What's a search? Why a search algorithm? Informally speaking, a search algorithm, unlike other transversal technique, it has brains. What it means is that it is really a smart algorithm which separates it from the other conventional algorithm. This fact is clear in detail in below sections, and it is also worth mentioning that many games and web-based maps use this algorithm to find the shortest path very efficiently. Explanation: consider a square grid having many obstacles, and we are given a starting cell and target cell. We want to reach the target cell from the starting cell as quickly as possible. Here, a search algorithm comes to the rescue. What a search algorithm does is that at each step it picks the node according to the value f, which is a parameter equal to the sum of two other parameters g and h. At each step, it picks the node cell having its lowest f and process that node cell. We define g and h as simple as possible below. G equal to the movement cost to the move from the starting point to a given square on the grid, following the path generated to get there. H equal to the estimated movement cost to move from that given square on the grid to the final destination. This is often referred to as a heuristic, which is nothing but a kind of smart guess. We really don't we really don't know what the actual distance until we find the path, because all sorts of things can be in the way, walls, water, etc. There can be many ways to calculate this edge, which are discussed in the later section. Algorithm: we create two lists, open list and close the list, like this extra algorithm. Initialize the open list, initialize the close the list. Put the starting node on the top list. While the open list is not empty, find the node with the least f on the open list, call it queue. Pop queue of the open list, generate queue as 8 successors and set their parents to queue. For each successor, if successor is the goal, stop search. Else compute both g and h for dot g equal to q dot g plus distance between successor and q. Successor dot h, distance from goal to successor. This can be done using many ways. We will discuss three heuristics: Manhattan, diagonal, and Euclidean heuristics. Successor.f, successor.g plus successor.h. If a node with the same position as successor is in the open list, which has a lower f, than successor, skip the successor. If a node with the same position as successor is in the closed list, which is a lower f than successor, skip the successor. Otherwise, add the node to the open list and push q on the close the list end. while loop. So suppose as in the below figure, if we want to reach reach the target cell from the source cell, then the A search algorithm will follow path as shown below. Note that the below figure is made by considering Euclidean distance as a heuristic. Heuristics. We can calculate G, but how to calculate H? We can do things either calculate the exact value of H, which is certainly time consuming, or approximate the value of H using some heuristics less time consuming. We will discuss both of the methods. Exact heuristic, we can find exact values of H, but that is generally very time consuming. Below are some of the methods to calculate the exact value of H. Pre-compute the distance between each pair of cells before running the search algorithm. If there are no blocker cells obstacles within, we can just find the exact value of H without any pre-computation using the distance formula Euclidean distance approximation heuristics. There are generally three approximation heuristics to calculate H. Manhattan distance. It is nothing but the sum of absolute values of differences in the goals x and y coordinates and the current cells x and y coordinates respectively. That is H equal to ABS current cell dot x goal dot x plus ABS current cell dot y minus goal dot y. When to use these heuristics, when we are allowed to move only in four directions only, right, left, top, bottom. The Manhattan distance heuristics is shown by the below figure. It is the figure where it has been shown. Diagonal distance. It is nothing but the maximum of absolute values of the difference in the goals x and y coordinates and the current cells x and y coordinates respectively. Dx equal to ABS current cell dot x goal minus goal dot x dy equal to ABS current cell dot y minus goal dot y x equal to d into dx plus dy plus d2 minus 2 into d into minimum of dx comma dy where d is length of the each node and d2 is the diagonal distance between each node, usually square root. When to use this heuristic? When we are allowed to move in 8 directions solely, similar to moving in chess. The diagonal distance heuristic is shown by the given figure below. Euclidean distance. As it is clear from its name, it is nothing but the distance between the current cell and the goal cell using the distance formula h equal to square root cell current cell dot x minus goal x goal x into 2 plus current cell y minus goal y into 2. When to use this heuristic? When we are allowed to move in all any direction. The Euclidean distance heuristic is shown by the below figure. Assume red spot as source cell and green spot as a target cell. This is the figure. Relations with other algorithms is a special case of a search algorithm where x equal to 0 for all nodes. Implementation, we can use any data structures to implement on open list and a closed list, but for the best performance, we use a set data structures of CSTL. Implementations are similar. The implementations are similar to algorithm. If we use a Fibonacci heap to implement the open list instead of binary heap, self-balancing tree, then the performance will become better. Average time to insert into open list and to decrease K. Also to reduce the time taken to calculate G, we will use dynamic programming. Limitations. Although being the best pathfinding algorithm around, a search algorithm doesn't produce the shortest path always, as it relies heavily on heuristic approximations to calculate H summaries. So when we use BFS over A, when we to use to find the shortest path, we can summarize this as below. One source of one destination use search algorithm. One source all destination use BFS. Use Bellman between every pair of nodes. Floyd Marshall Johnson's algorithm. Thank you.